Are you into puzzles, guys? I don't know about you, but honestly, I hate them. Every time I grab a puzzle box, I'm like, oh, this is gonna be awesome, the perfect way to kill time. But after a couple of hours of forcing pieces together, my patience just runs out. Maybe there's something wrong with me. And you know what? I thought puzzles just weren't for me. But then I saw this. It's this insane robot by Mark Rober that solves puzzles faster than a world champion.
This is Jigsaw. He's a friendly little robot that's really good at only one thing: putting together any jigsaw puzzle, no matter how complicated, really fast.
It crashed a two-time Guinness World Record holder, Tammy McLeod, beating her speed by 200 times. This is what I've been missing for the perfect Friday night. Imagine this: friends, craft pizza, puzzles, and a robot helping you crash the puzzle faster than anyone else. But here's the catch: this robot will not be helping me carry out my evil plan, cause it's not faster than a human. But hold up, we've seen in the video how it takes on the giant puzzle, finishes it in just 4 hours, and leaves the world champion way behind. Yeah, but here's the kicker. Not many people know what Tammy herself had to say about all this, which honestly isn't surprising since her video only got 8K views.
But I've actually solved 1,000-piece puzzles in under 4 hours.
But wait, why does the video make it look like the opposite happened? Who's actually faster, the robot or the human? Let's take a closer look, and I promise you're gonna be just as shocked as I was when you see what's really going on. In the comments under Mark's video, a bunch of people started guessing that the secret might be in a white puzzle. David Murray from the 8-Bit Guy channel even threw out the idea of a rematch with colored puzzles. And based on the 48,000 likes, it seems like a lot of people were on board with that. And honestly, it makes sense. We're all used to doing puzzles with pictures on them. I mean, who in their right mind actually picks out a white puzzle on purpose? Okay, maybe a few people who want to test their nerves. But really, wouldn't it make way more sense to hold a competition with the classic colorful puzzles we all know and love? Plus, Mark himself said that the robot, unlike us, doesn't care at all about what kind of puzzle it's putting together.
Way harder to solve for us humans, it would make no difference to Jigsaw.
Or is there actually a difference? In her video, Tammy dropped an interesting detail.
To optimize the computer vision capture, the puzzle is all white.
Optimizing computer vision? So maybe color did matter for the robot, and the white puzzle wasn't just a random choice after all? But Mark himself said they use an approach where they focus on the shape, not the image.
We took a much more simple approach by completely ignoring what was printed on the puzzle and just looked at the edges.
So, does it really matter what color the puzzle is for the robot? To get to the bottom of this, we had to dig into the document and check out the program code that Mark kindly made available to the public. And boom, we found the answer! Here's how it actually works. A puzzle is laid out on the table, ready to be assembled. The robot starts by taking a series of pictures, recording the coordinates of each piece. Here where things get really cool. The robot starts matching puzzle pieces. If it were us, we'd be sitting there trying to fit random edges together, one piece at a time. The robot kinda doing the same thing. It breaks each piece down into 4 edges, then compares them to find matches. Now, if I was doing this, I'd have to try a ton of pieces before I finally found the one that fits. That takes time for us and the robot. Since this is a speed challenge, the process had to be simplified and optimized. For us humans, there's no magic tricks. We just try pieces randomly. But computers? They've got way more tools to work with. One of those tools is comparing the length of puzzle edges. If an edge clearly doesn't match, that piece gets tossed out right away. This saves a ton of time and keeps the robot from wasting energy on pieces that obviously won't fit. Next, the robot stacks the remaining pieces together and calculates how well their edges overlap. If the overlap is almost zero, boom! it's a match. My colleague Shane from the channel Stuff Made Here built a similar puzzle-solving robot. In his video, he dives into all the nitty-gritty details like how the algorithm identifies key points on curved puzzle edges or handle rough-cut shapes. He even pulled out a vibratory tumbler to tackle some of the challenges. Now that's what I call creative engineering. But for now, we don't really need to know all the details. All we need to know is that the robot compares the outlines of puzzle pieces, finds the matching edges, and connects the right ones together. Have you ever wondered, though, how a computer even recognizes what a line is? Here's the thing. Computers don't see the world the way we do. If you zoom way in on any digital photo, it's just a bunch of tiny colored squares. Those are pixels, and every single one of them has its own unique combo of zeros and ones. By the way, this is red. This is how it looks like to a computer.
Do you always look at it and code it?
Well, you have to. You get used to it. I don't even see the code. All I see is blonde, brunette, redhead.
Okay, now that we understand how a computer sees the world, let's figure out how to teach it to pick out the puzzle outlines from a bunch of pixels in a photo. The first thing that comes to mind is to paint the background one color and the puzzle another. For example, make the background black and the puzzle white. But computers don't see colors, they just see numbers. So let's make it simple. Black equals 0, white equals 1. Now zoom in on the puzzle. Every pixel has 8 neighbors around it. If we add up the values of all these neighboring pixels, we'll get a total of 8. But what happens to a pixel located at the edge of the puzzle? Let's also sum up its neighbors and see that the total is smaller. That's because some of the edge pixels will always have black neighbors and their value is lower. So we can tell the computer that all white pixels whose neighbor sum is less than 8 are edge points. By calculating all such points, we'll identify the outline of the piece. Unfortunately, the world isn't perfect, and even pictures of completely black and white objects end up with shades of gray. Pixels like that will have values somewhere between 0 and 1. But hey, math doesn't care about imperfections, we just round them off. Anything less than 0.5 will be considered 0 or a black pixel. Any value above 0.5 will round up to 1, making it a white pixel. And just like that, we've brought this messy, imperfect world a bit closer to perfection. Of course, I'm simplifying it for clarity. In reality, it's a bit more complicated, but that's the general idea. Alright, now we can take the puzzle, figure out the outlines of the pieces, and start matching them. But what if the puzzle pieces are colorful? Well, the first thing we do is turn the image into black and white. This makes it easier to work with. All that extra info like colors just gets in the way. It's kind of like Zen. To focus on what really matters, you've got to let go all the distractions. Looks like programmers really got this Zen thing figured out. But honestly, it doesn't look much simpler at first. Just a bunch of gray blobs and patterns that don't make much sense. You'd probably think, how are we supposed to calculate anything when every gray pixel is slightly different? But look closely, we still have a solid dark background. Using the same principle of summing up neighboring pixel values, we can find the outlines again. Since black equals 0, adding up black pixels will always give us 0. But when our pixel is next to brighter neighbors, the sum will be greater than 0. And this way we can once again calculate all the points that make up the needed outline. You might argue that this won't work if the puzzle pieces have black parts in their design. In reality, that's not a big problem. Like I said before, the world isn't perfect, and we can totally use that to our advantage. If you zoom in on a photo of puzzle pieces with black designs, you'll notice that the background pixels are quite different from the black pixel on the puzzle piece itself. That makes the edge of the outline super easy to spot, and it means our little math trick is pretty legit. Obviously, working with colorful puzzles is trickier than just plain white ones. We'd have to throw in a few extra algorithms to handle errors. But what about speed? Would a robot actually take longer than a person to solve a colorful puzzle? Let's find out! Shane from the channel Stuff Made Here actually ran into some speed issues.
This is going to take a lot longer than I was expecting, like probably days.
But his robot was built a little differently.
I'm going to give the robot each piece one at a time. It'll take a picture of each piece with this very accurate camera with a telecentric lens. This takes about 8 hours.
Mark and his team managed to significantly optimize their algorithms, and their robot calculates everything much faster.
And after taking pictures of all the pieces, he once again actually solved the whole puzzle in a mere 55 seconds, which meant it was time to put them all together.
55 seconds? That's insane compared to a few days. And on top of that, they added some cool tricks for cleaning up the images. Just like in real life, photos aren't always perfect, and sometimes artifacts can appear that might confuse the computer. To make sure everything works smoothly, the programmers added extra algorithms to deal with those issues. Even if these extra steps for colorful puzzles make the calculation take twice as long, we're still taking 2 minutes tops. Honestly, I don't think this additional minute is going to hold us back too much. Bottom line, the robot doesn't care what kind of puzzle it's solving. With just a few tweaks, it can handle colorful puzzles just as fast as black and white ones. So, that myth is officially busted. Adam, you're on.
Totally busted.
But there's this one little catch. For humans going up against the robot, the difference is very real.
And for a human, solving a puzzle by shape is one of the last resort techniques because it's one of the slowest.
And no, that's not an overstatement. Tammy showed on her channel how she puts together a white puzzle, and honestly, it's insane. The first step is sorting all the pieces into groups with similar shapes.
There was quite a nice variety of shapes. In a grid cut puzzle like this, there are normally 6 shapes.
One group has 4 tabs, another has 3 tabs and a concave edge, and so on. And guess what happens next? You grab a piece that might fit, try it out, and repeat until it clicks. And then you keep doing that for every single piece. When we have a picture, it's super easy to toss out all the pieces that don't fit and pick the right one. But honestly, we humans aren't that great at spotting small differences in shapes. Let's see for yourself. Try to guess which of these puzzle pieces fits perfectly here. You'll most likely fail, unless you randomly pick the correct piece. It's just not what we're built for. Our eyes are wired by evolution to notice big objects, textures, colors, and faces. We're great at telling ripe fruit from unripe, spotting moving objects, or even finding faces in clouds, on rocks, or burnt toast. But when it comes to spotting the tiniest details in geometry, yeah, not so much. Tammy took over 2.5 hours to put together a 250-piece white puzzle. A robot, on the other hand, thrashed a 1,000-piece puzzle in just 4 hours. That's not just faster, it's like a Ferrari blowing past a bicycle on the highway. But with colored puzzles, it's a different story. On her channel, Tammy finished a 1,000-piece colored puzzle in just over 2 hours. Now that sounds like a win!
But I've actually solved 1,000-piece puzzles in under 4 hours. So until the robot learns some other solving techniques, it's not going to be the human on a puzzle that's not all just one color.
Back in 2020 at the British Puzzle Companionship, Sarah Mills solved 1,000-piece puzzle in just 1 hour and 40 minutes. That's truly phenomenal! So who's the real puzzle master? The robot or us, humans? The answer is more complicated than it seems. Imagine being challenged to a wood carving contest against a woodpecker. These guys were born to make holes in trees. Meanwhile, the best we can do with our bare hands is maybe snap a twig or two. And while you're busy figuring out how to make a basic tool, the woodpecker already drilled a dozen holes. So yeah, you'd totally get destroyed in that challenge. But does it really mean woodpeckers are better at woodworking than humans? These birds are awesome at what they do, no doubt about it. But look around. Tables, houses, even ships, it's all human handiwork. We do things with wood that are downright unbelievable. So let's be honest, nobody's better at woodworking than us. So why would we lose in a direct competition? It's all about the contest rules. They're stuck in a way that doesn't give both sides a fair shot. If you tilt the balance in your favor, you can win any competition. For example, if participants were allowed to use power drills, you'll undoubtedly win. Technically, the woodpecker could use the drill too, but well, it's a bird. Birds aren't exactly tool pros, they don't even have hands. So, equal conditions don't necessarily mean balanced conditions. and depending on where you tilt the scale, the winner could be a robot or a human. When it comes to white puzzles, robots are undeniably in the lead. They can solve them way faster than we can. But with colored puzzles, robots don't stand a chance. Or do they? Is it possible to speed up a robot enough to compete with a human even in assembling colorful puzzles? Alright, to figure this out, we first gotta answer another question. What exactly is the robot doing with those 4 hours? As we've already discovered, the calculation takes about a minute. But what about the remaining 3 hours and 59 minutes? First and foremost, of course, it's the photos. Mark mentioned that initially it took them 10 minutes to capture all the images. But objects that were at an angle to the camera didn't have perfect shapes and instead showed distortions like this. This is called the parallax effect. So they had to shrink the shot zone to a smaller area right in the center, where nothing gets messed up. That means they needed a lot more shots, and it went from taking 10 minutes to a full 90 minutes. The world record for puzzle assembly is only 1 hour and 40 minutes, which means we only have 10 minutes left to finish. To pull it off, we'd have to lay down one piece every 1.5 seconds, and that's just impossible. If we want to win, we have to speed up. The trick is to use a telecentric lens like Shane did. It fixes those distortions, making the shapes in the photos more accurate. Mark actually mentioned this, but they decided not to use it. Here's why.
We chose a smartphone over an industrial camera sensor with a telecentric lens because it told a better story, and we felt like making things harder for ourselves.
Well, okay. I don't think we can hit that perfect 10-minute mark, but hey, getting it down to 40 minutes feels like a realistic goal. That will give us about an hour to piece the puzzle together. And that's a problem because the robot currently takes a whole 2.5 hours to do it. My first thought, just make the machine lighter so it can move faster. Jigsaw's moving part is ridiculously heavy, plus it's carrying tons of extra stuff. Originally, this wasn't a robot at all, but a standard CNC machine designed to chew through various materials. That's why it's built to be sturdy, but this kind of design is far from ideal when it comes to speed. What we need is something lighter and more flexible. Something that can work fast and get the job done efficiently. For example, the print speeds of modern 3D printers are now approaching 1000 mm per second. That's so fast, even a camera struggles to keep up with their movements. But 3D printers are way too small for what we need. If we're working on smaller puzzles, a compact laser engraved frame will do the job perfectly. And for larger puzzles, we can go with a bigger laser system. This is sturdy and accurate, but also optimized for the high speeds required for engraving. Their frames are significantly smaller and lighter than a CNC machine. But even if we lighten the frame, it's still gonna need some fast motors to keep things moving. Mark mentioned they use highly precise motors.
Once we did this, we saw it could accurately place a puzzle piece down to 0.0005 inches.
Our hands have a precision of about 0.004 inches. While human precision is comparable to a strand of hair, the robot's accuracy is 10 times greater. Its error margin is about the size of a single red blood cell. But who has ever wondered why such precision is needed? After all, the more precise the motors are, the slower they become. Have you ever struggled to place a puzzle piece in its spot? I hope not, just like me. For us humans, our natural precision is more than enough for puzzles. So why does the robot need it, even at the cost of speed? It's because the robot assembles puzzles completely differently. We rely on what we see in real time. The robot? It only sees the pieces when it snaps photos. Then it memorizes their shapes and positions on the table, assembling them purely from memory. It's kinda like if someone's told you to memorize where all the pieces are, then made you close your eyes and try to put them together. And since the robot can't cheat by sneaking a peek, it has not only remembered where each piece is, but also moves super accurately to avoid messing up. Now you might be thinking, what's the problem if the robot shifts by like 0.0005 inches each time? That's only a tenth of the width of a human hair. No big deal, right? But here's the catch. That tiny mistake adds up with every piece. After placing 1000 pieces, that no big deal turns into half an inch of misalignment. And that's why building blind without super precise motors is pretty much a no-go. Modern robots like those from Boston Dynamics don't have this problem anymore. They got eyes, cameras or lidars that analyze their surroundings constantly. They don't need to rely on memory or flawless movements. If something's off, they see it and fix it in real time. But the jigsaw robot can't do that. If a piece is out of alignment and doesn't fit, it just keeps jabbing it around trying to force it into place. It'll keep doing this over and over until the piece finally clicks in. Obviously, this slows down the entire process. So now we've got a choice. Either figure out hacks to speed things up, or upgrade it with the ability to see like its cooler, more advanced robot relatives. Will all of this help the robot beat a human? Theoretically, yes. With all the tech we talk about, the robot's speed might get pretty close to the world's fastest puzzle solver. And that would be an absolutely spectacular showdown. I'd love to watch a battle like that. But sadly, I don't have Mark's kind of resources to pull off something that big. So if you want to see a match like this, leave a comment on Mark's video saying "We want a rematch" and share this video with your friends. If enough of us pick up, who knows, maybe Jigsaw will return for an epic sequel.